There we go. All right, I will begin with a word of prayer. So get up here. Everybody ready? Dear Father, we thank you for this day. We thank you for this time we have to meet together, to study your creation. Help us to glorify you, what we do this day, Lord. In your name I pray. Lord Jesus, amen. Caleb, Jacob, Austin, Lydia, Davey, Brian, no Brian, Sam, sorry, I should have spun it, Ernesto. No, how convenient.
Oh, nice.
So, yeah, your physics grader brought me these shortly after class Monday. So I thought yesterday I'd bring them, and I brought them to class here, and I promptly forgot to give them to you. So, anyway, there you go. So, any questions about anything before I get going here?
What's the answer to life universal?
42. No, I think it's to glorify God. I think that's probably a better answer. Yeah. Although I will say 42 does come up a lot. Let's see here. All right, so let me do an example which should be helpful for you guys. So here's an example. Suppose you have f of x is equal to the summation n equals 0 to infinity of, let's say, Cn times x minus 2 to the n power, and f of, let's say, 5 converges, but f of, oh, I don't know, minus 10 diverges. Okay? Question is then, find smallest and the largest possible IOC. Possible given the data, all right? So this problem, you have a homework problem like this, right? So let's talk about how to solve it. It's actually not hard. You have to have the right ideas, though. And it's really just a straightforward consequence of the theorem that we had about the domain of a power series, right? So the way I solve this problem is I make a picture, all right? And this picture is the number line, right? And on that number line, I first of all put the center, which is x naught equals to 2, right? Now, more recently we've been using a for the center, right? So is the center a or is the center x naught? The answer is the center is whatever you want to label it, all right? So early on, it was convenient to me to label it as x naught. Later on, since I'm writing a over and over and over again, it's easier to write a. But for me, I don't know, it's just, you know, a particular vice of mine. Writing x sub naught makes me think of a fixed point. And the trouble with the letter A is that we also have this word A. You know, so as you as you write something, it's sometimes hard to tell if that's the variable a or if it's the word a. You know, but anyway, you guys don't watch Happy Days so much, so that's not much of an issue. Okay, so and then what I do is I go, okay, so what do I have? Well, I've got 5 is a place where it converges, right? So that's here. What does that mean? Think about this. The possible domains are what? They're connected subsets of real numbers, right? And it's more than that, though, right? They're connected subsets of real numbers, but they're also symmetric about the center point, right? So what that means is that if I've included 5, right, in the domain, that automatically includes, how far is this? 3, right? So that means I have at least 3 in the other direction, which takes me to where? -1, right? And I'm drawing an open circle there because what did we learn about the endpoints? They're not what? They're not guaranteed, right? The interval of convergence may or may not include endpoints. But if 5 is included, the radius of convergence is at least 5. Not 5, at least 3, right? So what's the smallest interval of convergence that's possible? What did you say it was? It was -1 to 5. Now which do I include? Which do I exclude? Not including 1, including 5, right? Why is 5 included? Right. Why does it converge at 5? Because we said so, right? Don't think too hard about this. It was given in the problem, all right? It was given. Then what? Well, I also have other information, right? And the other information, and admittedly, if this other information had bearing on what we'd already written, then we'd have to adjust what we've already written. It just turns out it won't. Okay? So like logically, I'm assuming something here. I'm assuming that what I'm about to do won't affect what I've already done. Which, interestingly enough, is how physics usually works. That's called decoupling. Now, from 2 -10, where's that? Well, that's like over here, not to scale, but here-ish, right? Diverges, right? And how does the theorem work? Remember, if it diverges at one point, it will diverge at every point beyond that as well, right? We never have a series which diverges like 3 away from the center, but then starts converging 4 away, right? That never happens. That's not the structure that the theorem we found. That's not how the ratio test informs us. So, if I can find a marker here. Past this point, right? These are all diverging, right? And what does this tell me? This tells me that the radius of convergence is what? Is not more than what? 12, right? Because this distance from here all the way over to here is 12. Because from 2 to -10 is 12 units. So if this is diverging, and that's 12 units from here, what's 12 units the other way? So it's definitely diverging over here as well. Okay? So what does that make the largest IOC possible, given the data? -10 to what? 20. Where did 20 come from?
I said 14.
Oh, you said 14. So 20 was in my mind. Okay, not a good sign. Hearing voices again, out loud. It's especially annoying when they cover up your voices. Let's see here. But you're supposed to listen to voices, right? Follow your heart. So, so says Disney. Ah, yes. The Disney princess. The source, aren't we all? God forbid. Do you believe in the cult of the one? What's that? Yes?
So, if you were given to us that like f of -20 diverges, which we know is true,
Mm-hmm.
then wouldn't the IOC also expand it if you tell us that?
If I told you if you had additional information, if you knew that -20 was diverging, well, it depends on what you know. If you don't know this and you know -20 is the divergent point, then that would change it. But since we know -10 is diverging, if I tell you -20 diverges, that doesn't change a thing. And this, with what's currently given. So the question that we should answer though is -10 or 14 included, excluded? What's the deal?
They're excluded.
-10 is given to us to be excluded, right? Because that's a point of divergence. The IOC is the domain for the power series, right? That's what it is. So 14, if we want it to be the largest, we would like to include it, right? Because remember, what happens here does not have any bearing directly on what happens here for an arbitrary series. Now, if you have a geometric series, their fates are linked, right? Geometric series have a domain which is open. It's you know, the geometric series, the domain's like this, right? So what happens on one side happens on the other for geometric series. But for arbitrary series, this is not the case, right? Generally, you could have a left, you could have a right, you could have both, you could have neither. It just depends. But the good news is the interval of convergence, it always either looks like this or like this, right? Or like this, or like this, or like that. Them's your choices if you allow for infinity, right? Although the infinity has to go here, right? One of the other choice is this. These are the patterns where x naught's the center. Yeah.
So how do you know it converges at 14?
Well, the question is, what's the largest? So the best it could happen is if it did include, I mean, we're asking what's the largest one? Largest possible one, so that could happen. It also might not, right? Just like it also might not happen that all of this, like all of this might diverge as well, right? In principle, like you could lose all of these points because the smallest IOC is this.
It's just a what if
It's
question.
yeah. So possible intervals of convergence with the given data are anything between these two extremes. So I hope that should pretty much demystify that homework problem, right? But the purpose of that homework problem is for you to take stock of what the interval of convergence theorem really says, right? So you know what you're looking for. And by the way, it's not the same for other kinds of series. Like if you take a series of, you could take a series of things like the square root function plus the 3/2 power function plus the 5/2 power function plus the 7/2 power function plus and so forth and so on. These kinds of series appear naturally as the solution to certain kinds of differential equations. And if you do study those kinds of series, the interval of convergence are like rays that go from like the center of it to infinity or minus infinity for those ones. So the natural domains for other kinds of series are not like this necessarily. I should give you a definition. I kind of owe this to you. So if we have the sum, let's say a sub n equals 0 to infinity, times the sum, let's say, I don't know, use a different letter, j equals 0 to infinity of b sub j. All right, then how would you define the product of two series? Like, I was doing it last time, basically, all right? I assumed a definition, essentially, in our calculations. And the definition I assumed was essentially this, that when you multiply two series, you go order by order from like smallest to largest order, basically just that. So if you think about, you could write this out, and it kind of becomes obvious what you're going to do. So it's like this, and I'll write it with the plus dot 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 notation just for a second, because I think that'll help you. If I just wrote down the series formula here at the end, it would probably just be dark magic to you, right? Which is bad, right? We're still against dark magic at Liberty for now, right?
For now, I think.
For now.
We'll probably take a couple years.
How about Dungeons and Dragons? How do you guys feel about Dungeons and Dragons?
It's the good kind.
That's the good kind of witchcraft? Okay. So like Harry Potter then?
Yeah.
Oh, okay. Okay, good. So let's see here. So A0, A0, P0. So that's the lowest order thing, right? And then what I would do is I would look at A0 times B1 plus A1 times B1 plus, A2 times B0, something like that, right? And, oh, my bad. Sorry, guys. I'll get with it here in a second. I meant to put A0, B1 plus, my bad. Dummy. Me, not you. A1, B0. And then I will do like A0, B2 plus A1, B1 plus A2, B0, something like that. It's just a, yeah?
Just the order of series for the multiply matter.
Yes.
Terms.
It does. In fact, this wouldn't be ambiguous. Depending on so the convergence of the series matters. For this to be well-defined, I need that at least one of these series is absolutely convergent. It turns out that if I have one of these series is absolutely convergent, then what I'm writing down has meaning. If they're both conditionally convergent, though, if you wrote it differently, it would give you a different answer. Yeah, there's that. But so anyway, so if I write a formula for this, just like a stone cold formula, here's what it looks like. The sum n equals 0 to infinity. The sum, let's see here, k equals 0 to n, I believe. And then I just I give myself an a sub k and a b sub, I want to say n minus k. I think that'll do it for us. So that would be the definition of how to multiply series. Again, I do need to assume one of them is absolutely convergent. See what this is doing? It's going like, for example, for n equals to 0, this is just A0, B0, right? For n equals to 1, this is 0, 1, and 1, 0, and that's it, right? And and it just keeps picking up. So these terms right here would be for n equals to 2. See, because basically the sum of this index and that index is always n. You have k plus n minus k. It's always like all of the things up to that many orders. So when we apply this to power series, it's more interesting. See, because when you're looking at, say, the sum n equals 0 to infinity of, say, a sub n times x minus x naught to the n power times the series j equals 0 to infinity of, let's say, b sub j times x minus x naught to the j power, well, then that's equal to the sum n equals 0 to infinity of, what is it? Well, apparently the sum k equals 0 to n of, so what's going on here in this game I'm playing is that everything I'm thinking of here becomes playing the role that a sub n did in my, up here. And this all plays the role that b sub j did up there. So over here, I get what? I get a sub n, I get a sub k times b sub what? N minus k And then I get x minus x naught to the what power? Let's see what happens when you multiply a sub, man, I should have used different letters. My bad. The easy fix here is to put bars on these ones down here so you don't get lost in the difference. Let me just do that. So sorry, guys. I'll put bar on this one, and this one, and this one, and this one. All right. So then I don't need quotes. This is a sub n, and this is b sub j. No scare quotes, like that. And so what is a sub n? A sub k times b sub n minus k is actually equal to what? It's equal to a sub k bar, b sub n minus k bar, times what? Times x minus x naught to the k power times x minus x naught to the n minus k power. All right? And how does that simplify? See, that simplifies, right? What is that? That's just what? That's just to the n power, right? And so actually, this is the definition we're actually interested in right here. There's the definition of how to multiply power series right there. But it is essentially just an application of how to multiply series. Which I don't think I ever made you do before, did I? Because I think you guys you had enough on your plate without multiplying these things, right? It is kind of funny, though, if you think about it, because did multiplying polynomials ever really give you much pause before? Not really, right? It starts to get interesting here, though, when your polynomials have no end, you know? I believe this has a name. It's called the Cauchy product. Who's Cauchy? What's that? A what?
Relative of Yoshi.
A relative of Yoshi. I was not expecting that. I feel like that has given me license to say the following things. What buildings are untrustworthy?
I don't know.
No one knows. Libraries. Yeah, that's right. What do mountains use to stay warm? Blankets of snow is correct, but we call it a snow cap. Where can you buy a rainforest?
Amazon.
Very good. Let's see here. Why did the lettuce beat the carrot in the race?
Because it was a vegetable. Oh.
Because it was a vegetable.
Oh, God.
That is really bad. Wow.
No. Because he was ahead. Let's see here. What did the snowman say to the other snowman?
Hello.
He said, "Do you smell carrots?" What's the best Mexican food to eat in the winter?
Arroz con pollo.
Oreos con pollo. That's not just for the winter, though.
That's year round.
It's year round. Although I might argue taco salad. But anyway, yes. No? Burritos. Yeah. You have to enter the 10-year-old mind to understand these. I have found out, though, that these jokes land much harder in my college algebra class. Like, I get much more traction there with these jokes than here. Like, I go figure. I think physics is laughing harder at these jokes too. So you guys are, yeah, but you're the good part of physics. Don't tell the others. I'm joking.
Yeah.
I think I'm joking. Do you guys have other questions about homework before I go on? Yep.
Problem 100.
Problem 100. Ah, I've lost it. You'll have to tell me what I've done to you.
It says find the first three non-trivial terms in the power series centered at x naught equals 1, where f of x equals 1 plus x squared times sin x.
All right, so let me make that, let me take your problem and trade you x naught equals to 2 and f of x equal to 1 plus x squared cosine x. Okay, but anyway, same idea-ish. So problem 100 now. So you want the center to be x. So there's various ways. How many terms did I say? 3? Okay, so first of all, point of order, you could differentiate this 3 times and just use Taylor's theorem. That wouldn't be too much work, right? That is not how I'm going to do it, though, because differentiating this 3 times does not give me joy. I will use my trick. And the trick that I will use, oh man, see, I don't know. This is right on the bubble as opposed to whether I should use Taylor's theorem or not directly. Let's see here. So I will use the trick. So this is 1 plus, that is x minus 2 plus 2, quantity squared, parentheses, cosine of x minus 2 plus 2. So what I do, if I want to center the expression at something, I just add 0 as appropriate to make factors of x minus 2 appear. All right, so to start with, you've got, 1 plus parentheses x minus 2 quantity squared plus 4 times x minus 2 plus 4 close bracket. And that's it. That's all she wrote. Like that is the sum total of what comes before the cosine for mine. Does that make sense? I just foiled it out. What I'm using is, algebra. So this right here, I'm thinking of this as A. Let me tell you my internal logic here. This is A and B. If I have A plus B squared, how's that go? The way it goes is this: A squared plus 2AB plus B squared. I know this. I use this. I don't foil it. I apply this identity. It's one of the things that I have hardwired in my brain. And so I just use that here. This is A squared. This is 2AB. But it's like, so 2 times 2 is 4. X minus A. 2 squared is 4. Like this. Now, of course, I'm going to want to combine the 4 and the 1 to give me a 5, right? That'll be like the next step. How about this here? Well, that is the cosine of x minus 2 times the cosine of 2 times the sine, or minus rather, sine of x minus 2 cosine of 2. Oh, excuse me, my bad. Sine of 2, right? So this is the adding angles formula for cosine. Now your problem, you're going to want to use the adding angles formula for sine, right? I think. Now what was the first 3 terms? Yeah? First 3 terms. So you have to ask yourself, oh, we're not quite ready yet. We need to do what? Expand cosine and sine in their Maclaurin, well, not Maclaurin here series, but Taylor series. So Taylor's like finally getting the respect that I'm due. Let's see here, those stupid Maclaurin series. Let's see here, plus x minus 2 squared. As far as I know, there are really no objects named Nicholas in mathematics, so you're safe on that.
I'll make something up.
You'll make something up. I like it. Okay, so cosine of 2, right? And then this gives me 1 minus 1/2 x minus 2 squared, and then so forth and so on. And then minus, let me put a closed big parentheses here, and then minus the sine of 2, open another big parentheses. And let me make this larger parentheses curly so you can see the difference. Sine of 2, and that gives me x minus 2 minus 1/6 x minus 2 cubed plus dot 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 dot. And I think that's going to be enough for us. All right. Yep.
Did you plug those into that given cosine and sine formula?
Yes, I plugged it into the known Maclaurin series, making the substitution u equals to x minus 2. Yeah. Like I said, you got to memorize those, otherwise it won't make sense what I do. It's true. Now the question is, as you multiply these, right, how do you do it? Well, I kind of told you in the middle board. We do it order by order, right? Lowest order to first order to second order. So is there any constant in all this? How can you get the only way you can get a constant is from a constant times a constant, right? So look at it. There's a 5 here, and there's a 1 here. These, order 1, order 3, right? So the only way to get a constant is from that 1 times that cosine 2, right? And so the constant term here is 5 times the cosine of 2. Hey, there's one non-trivial term, 2 more to go, right? By the way, that makes sense. That checks with what we expect, because what do we expect? We expect that, f of x should be what? F of 2 plus f prime of 2 times x minus 2 plus 1/2 f prime prime of 2 times x minus 2 squared, da 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 da. And what is f of 2? Plug in 2, what do you get? 1 plus 2 squared, which is 5. 5 times the cosine of 2, which is, that checks, right? Checks. Now checking past there will require differentiation, which will beg the question, why didn't we just use Taylor's theorem to start with? So that's as far as I'm going to check. But what's next? So linear terms, yeah? To get a linear term, I've got this, right, times these. Anything else? I also have this 5 times this guy, right? Is there any other way? No, that's it. Just like up here, these were the only ways basically to get linear terms. It's that same idea. So at quadratic terms, there's 3 ways to get it. Either the constant times the quadratic, or the linear times the linear, which I think I missed last class, and you guys corrected me on it, didn't you? Let's see here. So plus what? What do I got? Plus 4 cosine 2, and then minus 5 sine of 2 close parentheses times x minus 2. All right. And then how about quadratic terms? I have the 5 times, so basically minus 5 over 2 cosine of 2, all right? And then I have minus 4 times the sine of 2. That comes from the x minus 2 term, if I haven't lost anything. And then finally, the plus cosine 2 close parentheses times x minus 2 squared plus dot 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 dot. So, like I said, I'm not 100% sold on this being the correct way to do this problem on a test. I think on a test, if you're solid in differentiation, differentiating this 3 times and evaluating it 2 is a faster path, actually, if you're good at differentiation. Yeah. This is a hard problem any way you slice it, though, right? It's, I mean, well, hard is perhaps too much, but it's not, you know, just trivial. There you go. Those are the first 3 non-trivial terms. Yes, sir.
If we were to differentiate and do Taylor's theorem, how would we center n times equals 2?
That's, see, to do Taylor's theorem, all you have to do is calculate f of 2, f prime of 2. So like f prime of 2 would have been, see, now you're going to make me check my work. All right. What's f prime of x? So if I differentiate, I'm about to differentiate your problem. Differentiate my problem, I get what? I get 2x cosine of x minus parentheses 1 plus x squared sine of x, and then f prime prime is 2 cosine x minus 2x sine x minus 2x sine x minus 1 plus x squared cosine x. And then you have to evaluate it too to do Taylor's theorem, right? So evaluating it too, what does it give me? So f prime of 2 apparently is four cosine 2 minus 5 sine 2. And what's f prime prime of 2? It's a little bit more of a mess, but if you, we should just put things together, right? I've got a cosine here, and I got a cosine here. When I plug in 2, what's that give me? This is a 5, right? 2 minus 5, so minus 3 cosine 2. And these are my sine terms. So when I plug in 2, I've got 4, so I get a minus 8 sine 2, yeah? Did I miss something?
The x equate 2 on the bottom answer, not on the top answer.
So your first expression.
Are you saying there's something wrong in the differentiation? What are we talking about?
No, on your, in the blue on the bottom.
Oh,
First, it was 4 cosine 2, take away 5 sine 2.
right.
Times x.
Oh, yes, yes. So, but I think that matches, yeah? Like what I'm trying to say is, this right here is literally f prime of 2, is it not? And this, as we discussed earlier, is f of 2, right? What do I expect this to be? But not f double prime of 2. 1/2 double of, that's the thing. Taylor's theorem says, like, Taylor's like, come on, respect my theorem. You got to divide by 2, right? And so these two things go together, right? What's 1 minus 5/2? And what's minus 3/2? So, so we're getting that this is minus 3/2 cosine of 2 minus 4 sine 2, right? So if you multiply that by 2, it checks. Good news, we can multiply polynomials. Woohoo! I mean, series, but, you know, as Dr. Kester used to say, Texas-sized polynomials, right? They're really big. So what do you guys think? What's the right way to do this problem? Taylor's theorem or multiplication of series? I think Taylor's theorem is better here. But if you disagree, I respect that. I'm on the bubble, like I said, for this one. Everybody got the sheet?
Sorry, for actual like problem, for actual problem, what
Uh-huh. Again, I think it's a wash. You can go either way. Yep.
What are trivial terms in this case? What would trivial be?
Trivial means zero. So like non-trivial terms means non-zero terms. And so these are the first three non-zero terms. Yep.
In the way that you did it, like without Taylor's theorem, how would you like determine like what to put in the like 4 cosine 2 minus 5 sine 2? How would you determine what to put?
Well, situational awareness, I got to think about where I'm going. And so as I look at the original function, I go, is it even? Is it odd? What's the situation here? Well, I've got, oh, that doesn't matter actually, my bad. Because that thinking is for 0. This is for 2. Okay, so that's not it's not helpful, right? And so, I mean, it could have gone badly if I had found out that actually the first order and the second order somehow conspire to be 0. Maybe I wouldn't have written enough, because then I would have needed, third order and fourth order. Have I written enough here to take care of everything fourth order? Not quite, right? Because I need to write the fourth order term down here to make sure I didn't miss something. So I say you try to be lazy. Try to get away with writing just enough, but check yourself, right? If you find yourself using something third order, you have to say, was I fair? Did I include everything up to third order and the other terms? Because if I didn't, I need to go back and put that there and take account of it. That's how I do it. I try to be lazy and then I kind of adjust.
Because like I get the second and third order and stuff. I was just confused. Like 4 cosine 2 minus 5 sine 2, that's equal to f prime of 2. But I was confused how you like decided that go to there.
This step came from?
At the bottom. Yeah.
Oh, this is just identifying. So this is Taylor's theorem. Taylor's theorem says if I have a power series centered at 2 for this function, the meaning of the coefficients has to be given by Taylor's theorem. It's non-negotiable. The 0th component is f of the center. The coefficient of x minus 2 has to be the derivative. The coefficient of x minus 2 squared has to be the second derivative divided by 2. Like this is Taylor's theorem.
Yes, sir.
Yeah. That's how I knew that.
Yes, sir.
I don't think that's at all obvious from the multiplying of these things.
Yeah.
Like the multiplying of these things doesn't, at face value, seem to have anything to do with differentiating once and then twice the function. That's part of the mystery and the beauty of this method. Let me show you guys something on the projector because it will help you with another problem. Oh man, I forgot to give you guys a quiz again. At some point, I'm going to get here early enough to print a quiz. Let's see here. Some point.
Don't worry about it.
At some point. Just give you credit. Let's see here. Where was I? What module are we in? This is the part of the semester where the modules in the week will get unaligned, but only in some of your classes because other people will have labeled this week 9, module 9. At some point, the micromanagers will notice this, and then it will become a university directive. This is module 9, week 10. Or with my luck, it'll be module 9, week 9, and I'll have to change everything. Where was it? Was this power series? Power series, right? All right. Oh man, I've only got 3 minutes. Son of a gun. Rats. Well, I will show you nonetheless. I was hoping I would have enough time to talk about the proof. Obviously not. So there's a bunch of stuff in the notes here on the, why am I in this browser? Oh, that's aggravating. There we go. So what I wanted to draw your attention to was one of the problems in your homework that is due. What? Oh, I'm a victim of my own older edition All right, fine. Chrome, have your way. All right, so I have examples like we done, and then, oh, come on, I've skipped past it, my bad. So back here, I have this example. Example 4.2 in the notes would be helpful to you on the example. One of the ones I think it was, you guys help me out, it's like what, square root, is it x over the square root? What is it? Is it one? I don't remember the formula off the top of my head. Did anybody have their homework? Oh, you guys all packed up.
X over the square, yeah, x over the square root of 1 take away x.
Okay, great. So this, if this expression right here, that is not in the ballpark of anything else you've done. And you do not want to differentiate this 3 times. It's much worse than what we were talking about over there. So how do you do this problem? You do it with the binomial series. See this, ignore the x, and just look at this as 1 over the square root of 1 minus x cubed. The way to do this is to think of that as 1 minus x cubed to the minus 1/2 power. So basically, make this 1 plus u to the minus 1/2 power, where your u is minus x cubed and your alpha is minus 1/2. What I derive right here is known as the binomial series. It's very simple. F of x, 1 plus x to the alpha, differentiate, 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 differentiate. You can easily see that you get alpha, alpha times alpha minus 1, alpha times alpha minus 1 times alpha minus 2, alpha times alpha minus 1, all the way to alpha times alpha minus n minus 1 if you take n-fold derivatives. And then if you plug in 0, that gives us the Maclaurin series for this. This has been known since Newton. Like, this is how Newton did a bunch of things. It's part of how Newton checked calculus, is he knew about this series. And, but anyway, this does many things. In the case that alpha is an integer, right, like a whole number, what happens to this series? What happens if you have like 1 plus x to an integer value? Think about it. What happens if you have at n equals to 10, you take 11 derivatives, what happens? It's 0, right? So this series truncates if alpha is an integer. So if alpha is an integer, this actually just becomes the binomial theorem. You guys have heard of the binomial theorem before, yeah? Yes, no? All right, we'll talk about this some other day. I see I'm talking to